All right, everybody, say hello to your orchestra. Say hello to the orchestra class.
Yo, Henry.
Hey, y'all! If you're watching this, good on you. If you're not watching this, then that means
make sure you like and subscribe.
Make sure you like and subscribe. And comment below. No, don't comment below. I don't want bots to start populating my videos.
That's true. That's true.
All of a sudden, random stuff start popping. Oh, dude, they're not great. Let's just say if you scroll down on YouTube, they do not look the best when you look at the comments.
Bro, YouTube comments are foul.
Instagram comments.
No, Instagram comments.
I never am on Instagram.
Instagram comments are crazy.
YouTube is the only kind of social media I do, and that's mostly just because I need to watch math videos. I just don't. I do not want to get on Instagram or Facebook or anything like that. It's dangerous.
YouTube Shorts.
No, that's even worse. Gosh, I hate YouTube Shorts.
YouTube Shorts. Not as bad as like.
I'm an Instagram girl.
No.
It's just about attention span stuff. Especially when you're younger, you can train your brain to absorb information in small bursts, which means that when you go to school, you're just going to look, pay attention for like 10 seconds and be like, what's the next thing?
You need the Subway Surfer connection.
You need, I think, yeah. What was it, like some guy was doing an interview and he was super nervous, and then all of a sudden the guy's like, wait, I think I can handle it. And he just uploads, he like looks up a video, he's like, right here, here's the game. He like starts playing Subway Surfer, right underneath his face, he's like playing it there. And the guy's like, oh yeah, I can do this now, this makes so much more sense. Anyways, so, one way that we can apply, calculus into physics is by looking at fluid force and fluid pressure. The story of the Great Molasses Flood of 1919, along with the calculation of fluid pressure using integration. So here's the story. On January 15th, 1919, at 1 p.m. in Boston, Massachusetts, a 90-foot high, 90-foot diameter cylindrical metal tank in which the Puritan Distilling Company stored molasses at the corner of Foster and Commercial Streets in Boston North End exploded. Molasses flooded the streets 30 feet deep, trapping pedestrians and horses, knocking down buildings and oozing into homes. It was eventually tracked all over town, even if it made its way into suburbs via trolley cars and people's shoes. This would take weeks to clean up.
Is this true?
Okay?
Yeah, it's a great molasses flood. It actually happened.
Yep. So, what we're going to do is we're going to use the information we know about this problem, and we're going to identify a couple of different things about it. So, the first thing is...
You just eat it.
A, given that the tank was full of molasses, weighing about 100 pounds per foot cube, so every foot cube is like every cube of 1 foot, so 1 by 1 foot cube, weighed about 100 pounds. So you had a 100-pound cube, and you fill that. And basically, think about it, you fill that into that entire cylinder, and that's how much molasses was in there. What was the total force exerted by the molasses on the bottom of the tank at the time it ruptured? So the first thing we're going to do, let's go ahead and I'm going to give you some formulas real fast. Make sure you have these down. The first formula is that pressure.
Can we do an oceanscape practice problem?
What?
An oceanscape practice problem.
Oceanscape practice problem. If you come up with it, why not?
Okay.
So, pressure here is going to be equal, so this formula, P equals fluid pressure. W equals weight density. And H equals depth height. So, here's our first formula. Our next formula is going to be F is equal to P, which again we already have, times A, where A stands for the area of the shape. So we need the area of this shape. So, for A, what was the total force? Well, in order to find the force, what do we need? We need the pressure. And in order to find the pressure, we need the weight and the depth. Well, let's draw this out. Now that I have these formulas, I'm going to go ahead and draw out a cylinder here, like so. I know what is the diameter of this cylinder? It is 90, so therefore the radius is?
45.
And then how tall is it? This is going to be 90. Okay? All right, awesome. So let's go ahead and fill in the information. I know that P is equal to, do we have the weight density? We do. What is the weight density of the molasses?
100 pounds per foot squared.
So 100 pounds per foot squared times, what's the height going to be equal to?
90.
90. So that's going to be 90,000 pounds per foot squared is the pressure.
Cubed.
No, squared. Because we took pounds. So this is actually important that Connor just asked. Why is it pounds per feet squared and not pounds per feet cube? Per feet cube? Because this right here, where we're taking this, what is 100? 100 is LB over FT. Sorry, LB over FT cubed, right? Times, and what is 90? 90 what? Feet. So what happens when we multiply feet by LB per feet cubed? We would get LB per feet squared.
I understand.
So now, we know that P equals WH. We already found this. We know that the pressure is equal to 9,000 pounds.
9,000?
It's equal to
That's
9,000.
funny, right?
Luke, it's equal to 9,000.
Well.
It's not over.
Dude, come
What the
on.
hell?
Okay.
Code it correctly if you're
My
going to
bad,
use
my bad.
Vegeta's. The Vegeta line is a very important and cultural moment for many of us men in this room.
Got it.
The what?
I never
The
watched
Vegeta
it.
line?
Never watched it.
It's over 9,000.
Oh, I didn't know what it
I
was.
remember watching that when I was like 9 or 10 years old. That was
Wait, what's
crazy.
that from Dragon Balls?
Dragon Ball Z.
Dragon Balls.
Oh wait, did we watch the bunny?
The what?
The bunny thing? What's it called?
Bugs Bunny.
Yeah, we watched Bugs Bunny.
I'll pick up.
That's what you're missing. That's what you're missing, y'all. You're missing Bugs Bunny and Cow Class.
Also, they better bring home the trophy.
For sure. All right, now we have our force is equal to pressure times area, right? So we know force equals pressure times area. What is my pressure here? 9,000. And what is the area of the cylinder? The area of the cylinder is pi times
2R.
45
Wait, what?
squared, because it's pi r squared area, not
Oh,
the area of the. What is the area? When we do this, we do a two-dimensional area, right? What are we looking at here, Connor? What was the total force distributed by the molasses on the bottom of the tank? So what's the bottom of the tank?
It's just a circle.
It's a circle.
Well, yeah, but I thought you were looking for the entire.
No, we're looking for just the area of that circle down there. Okay?
I just.
Not the surface area. Because we're looking for how much, because when you have it is bursting outwards a little bit, right? But it's mostly going, where's all the weight falling, Connor?
At the bottom.
Downward. There's still pressure going outwards that way. So this is equal to, multiply this out, how much pressure was being, and remember, you might have to do this as well. This is pounds per feet squared. What is area in? Area is in feet squared. So what happens when you multiply these two? These two are going to cancel. So what are we left with? Just pounds. And your answer should be
18,225,000 pi.
yep. Or I'm actually multiplied by pi.
Oh, so it is no over 9,000.
It is over 9,000. Yes.
Okay, good.
Wait, it's over 9. It's over 9 million.
That's all true.
57 million.
57,225,516.11.
26 plus 26.
I just rounded the nearest. Yeah, that's round there.
Is that how much it?
That is how much force was being applied to the bottom of the tank.
Holy butt, bro. What?
Yep.
Mr. Mullen, do I
That's like a molasses planet.
do I give off like that I was in orchestra? Does
Yes.
everyone-
Five.
Yes, no, it
You
does.
totally do. I thought you'd be
People who
gone.
were in the orchestra thought I was in orchestra.
I mean, I know you're not an orchestra. Like I personally know you're not an orchestra. I don't want to answer.
I thought you go. Are you an orchestra too?
I can't play instruments.
Really? There's no way.
No, but even people in orchestra were like, "You were in my class in orchestra," and I'm like, "I was never in orchestra."
All three of you give off orchestra vibes. Oh, shut up.
You give up orchestra.
Me?
Y'all all three.
Okay, y'all. So, also, have y'all been getting? Has anyone in here been getting? Maybe not. Maybe you're all too young. I keep getting spam texts about like job opportunities.
Oh my gosh, I get those all the time.
Yeah.
Timu. I got from Timu.
Yes, I do.
I've gotten like 6 in the past week.
Oh, they want you, Mr.
They were gonna give me
You should do it.
Timu doesn't want you.
Yeah, that's
Oh.
yeah.
My grandma even emailed me. She's like, my grandma told me like, Johnny, there are so many job offers I'm getting from Indeed and LinkedIn, and I'm like, those aren't real.
You guys are up.
I
I
got
got a job offer from Michael's and like rearranging.
Are you excited? I'm already getting offers and I'm not even out of high school.
So good luck working at Timu. Selling $1.
Okay, everybody. So, what we're going to do now is we're going to look at this next part. What was the total force against the bottom foot wide band of the tank wall? So what that's going to mean is I'm going to look down here and I'm going to create a little band down here like so. A little band.
Wait, like the Jonathan Holm band?
Dude, you can't say the
Johnny
first
Holm.
name.
That's
a
a give me a
demerit,
demerit
bro.
for that one.
Oh, my bad.
My middle name is Jonathan.
I apologize.
I'll give you participation points back up. But no.
Oh, yeah, actually?
Oh yeah, for sure.
You just
With that, his name is Jebediah.
No, my middle name is
What was I calling it? Oh, Jeremiah is what I called you for the longest time.
I love that.
Okay, all right, let's finish this off, y'all. We're almost done. Well, not really, but still. So, what we're going to do is we're going to partition
Oh, that's always goes well.
a depth band from 89 feet to 90 feet into narrower bands that have a length, that have a height of delta y. So I'm taking that 1 foot at the end and I'm going to start to cut like little slices off of it, kind of think of it like cross sections. I'm cutting out these cross sections, these circles, so we can kind of break it apart into an infinite number of things. And then we have, so we have into narrow bands, delta y, and depth y sub k. On each one. So the pressure at y sub k is going to equal W times the height, which equals, my height is just going to be W sub k. That's what my height is at that point. So I'm going to get 100 times y sub k pounds per feet squared. This is the pressure at each depth. You just take 100 multiplied by whatever that y value that you chose is, however much smaller and smaller you make it. We know that F is equal to pressure times air. We know that F equals P times A, which equals 100 y sub k times, and in this case now, what we're creating is kind of a rectangular band in this. It's hard to see it, and I don't love this right here, because that's why I don't love this problem. But the idea here is that we have this band that we're pulling out here.
Is this supposed to be like a smaller circle inside, or?
Like so. We're pulling out this like rectangular band right here. So you create this rectangular band. And I know that, how long is this across? 90. And the distance in between here and here is going to be, oops,
It's just like a stack of coins when you're pulling a coin up, right?
delta y. I guess that's a good way to describe it, I think, yeah.
Wait, how do you know it's 90?
Because what's the diameter of this cylinder? 90. So the whole thing across would be 90. Yep. So then we have here times 90 Pi delta y. I might have to look this up again because I looked this up just to make sure I could understand everything. But then again, this is why this is my non-area of expertise. We should get 90 pi delta y for some reason. Oh, it's 2 pi. Never mind. Sorry. Whoa. It is 2 pi rh that we use there. So instead of, it's not the rectangular band. It's just that we're looking at the surface area of the outside. We're not looking at the bottom anymore. We're looking at the area of the whole shape. So therefore, Connor, this is when we would use the 2 pi rh, right? So we've used 2 pi rh. How high is each band? 1. Or we would call this, well, we take that 1 inch band and we're looking at it specifically, but because we're cutting it into small pieces over and over and over again, that would be our delta y. 90 pi delta y, 45 times 2 pi. To get this here, I'm going to find a different problem so I can, this problem I can't explain as well, but another problem I can explain better. We would multiply these out, 9,000 pi times y sub k times delta y. And thankfully, because we have this here, notice we have a delta y, which means we can set up a what? An integral. So our force is going to equal, I'm looking from the 89th to the 90th down there. That 1 foot at the bottom is going to be 9,000, multiply those two, pi times y sub k, which is y, dy, which delta y changes into this, and y sub k changes into this.
Why can't we just do 0 to 1? Because it's the same thing as working from the bottom.
Because we're not looking at 0 to 1, we're looking all the way at the bottom.
But isn't that basic? Because if it's standing, 0 would be the ground, then the 1 would be just like how high.
No, because right now everything's pushed. We're not thinking about. You're thinking about it the other way. Where's all the pressure going?
The bottom.
Down. So here would be the top. This would be 0 to 1. Then you go to the bottom. That would be the bigger one. That would be where we get that.
Would it give
Yes,
a different answer?
Oh, sorry. It would give a different answer. Yes, a much different answer. Mm-hmm.
So you're looking for like the pressure of the surface area of like the bottom foot. Is that what you're looking for? Like I don't understand.
You're just looking at the pressure of the 1 foot at the bottom.
Yes, of the 1 foot at the bottom. Mm-hmm.
Okay.
Yep. That makes sense?
Yeah.
Okay. Oh, I've tried to explain. I actually did try to explain this to myself multiple times. Once I get really into physics, I just get a little lost. Always happens to me. Then we do this integration. I'm just going to say you can use Math 9, but honestly, do we need Math 9?
Yes.
This not really. This is just 9,000 divided by 2 times pi times y squared from 89 to 90. Or if you use Math 9, you would get 2,530,533. Okay, so what I want you to do now, we're just going to be working on different problems. Okay, so just so we can be clear, what I did here was because now we're looking at a cylinder and not just the bottom circle, we had to take this. We have the cylinder, which is 2 pi r, which is 2 times, I'll write it up here just so you can see it, 2 times pi times 45 to get this part right here. And then my h value is my delta y, because that's what I'm cutting the cylinders into smaller and smaller bits of. That makes sense. Okay?
How do you put it into the calculator?
You just put this into the
Was it
calculator.
supposed to be-
Math 9.
Yeah, but give me a different answer.
No, that's not. No, you put in the integral. That's already the integration. You already integrated it that way. You need to put the original one. All right, so what I want y'all to work on is 7 through 13. 7 through 13. So everybody, let's go ahead and turn to 7. I'll help you out with the first one. So, when you're doing this, you always need to use 2 equations. Really. So, when you're doing this, the first step is always going to be to find an equation for this graph here. Now, we will always be in terms of y. So can anybody tell me what's an equation we can use for this graph here?
I have a question about the public.
Yep.
If you integrate the equation we formulated from 0 to 90, you get double the answer we did from the first problem. Why is that?
Because we're not just looking at the pressure at the bottom now, we're looking at the pressure that is being exerted on the entire shape.
But if you did it from 0 to 90, wouldn't that just account for the pressure of the entire cylinder?
Yes, but again, this is the pressure. What are we looking at here? Right here, if notice here we did pi r squared. Here we're doing 2 pi r. Again, because this is only we only care about the circle at the bottom. Here we care about the whole cylinder. That makes sense. Again, if you are interested in any of these problems, I would very much recommend you go talk to Mr. Miller about any questions. I will answer as well as I can, but I cannot always. So my first step here, I'm going to formulate an equation to use for this. What is my equation?
Pi r squared.
Yep. 1/2 pi r squared. Good. What I'm talking about for an equation, though, is an actual equation for this graph. Because you want to remember, how do I graph a circle?
A times x minus h squared plus y minus b squared.
Exactly. Yep. Well, or an easier way to describe it would just be x squared plus y squared equals r squared. So we have x squared plus y squared equals r squared. So this is going to be x squared plus y squared equals what?
5 squared.
5 squared, which is 25. Now, what do I want to solve for in this case? We always want to keep that. This will always be in terms of y. So therefore, I'm going to solve for x. We will get x is equal to the square root of 25 minus y squared. So there I have my equation. Because what I'm going to do is I'm going to draw this rectangular band down here, like so. And I'm pulling this small part here. This is the part I'm pulling away. I know that this height is going to be delta y. And what is the x length going to be? How do I find the length from here to here? Isn't that just the x value?
Yeah.
Which is this right here. However, that's only one of the x values. How would I find the other one? We'd have to multiply it by? Because we only have this number right here.
Negative.
So I would have found the whole thing?
2.
We'll just multiply it by 2. Because this is going to be the same as that. Okay? So we get here. The next part is going to be this strip. This is the strip that we pulled out. We have x equals 2 times 25 minus y squared, because it is double that length right there. It is double that length. Therefore, what is the area of the shape going to equal, Connor?
What?
The area of the shape. What formula do we use? You already said it?
1/2 pi r squared.
1/2 pi times, and what's the radius of this shape? All right, so no, wait, sorry. Oops, sorry. This is if you look here, what do we have? Is that a circle or a rectangle right there? That's a rectangle. So we can actually just use 2 root 25 minus y squared. And what is the height of this rectangle? Delta y. So now we just need to find all our other stuff. For step 3, what is the pressure here? The pressure is P equals my W times H, which equals 62.4 times my height. My height is going to be y, where y is from 0 to 5. The y value is the height that we're looking at here. It's different than this delta y. The y I'm looking at is 0 to 5. That entire height right there. Then we can integrate it with this formula. F equals the pressure times the area, which is equal to the integral from, what are my bounds I'm looking at? Are we looking at x bounds or y bounds right now? Everything's in terms of y. So therefore I'm looking from 0 to 5. Then I'm going to go ahead and put in my equation. We have 62.4 y times the area, which is 2 root 25 minus y squared, which equals from 0 to 5 of 124.8y root 25 minus y squared. Go ahead and math 9 that. Oh, don't forget the dy, which is equal to.
How is it 124.8?
What's 2 times 62.4?
How do you do that?
Yeah.
Interesting.
0 to 5, and this is actually going to end up with a really nice number, which is kind of surprising. You look at this, you think this is going to be a mean one,
13.
but if you do this, you should get
Not quite.
8x root 25 minus x squared dx is, what do we get? Exactly 5,200. If you put it in your calculator, you'll see you get exactly 5,200. That is the force that the water exerts against the end of the tank. So, just so you can picture this, do we know what this looks like right here?
Bowl. Wait, what?
This is the vertical end of a tank. So imagine a tank that looks like a cylinder, but it's cut in half. Like just a vertical half of a cylinder. And then at the bottom of the tank, what is the force being exerted? There are 5,200 pounds of force being exerted against the bottom of the tank. Does that make sense?
Yeah.
Okay. Do we all kind of see how I worked through that? All right, this is where I'm going to let them go. Everyone say we had so much more fun than you.
We had so much more fun than you.
Now we're going to go watch Bugs Bunny while they do homework. Yeah, unfortunately, we don't miss Caleb. We do miss Isaac, though.